Good afternoon, everyone. Thank you for joining us for yet another exciting session under the GCRF Mine Dust and Health Network in collaboration with SAIMM and the Minerals to Metals Initiative of the UCT. So this afternoon, we're privileged to have Mr. Jay Colinet, all the way from the US of A, and he's going to be presenting to us on a very exciting topic relating to the escalation of black lung disease in the US and the systematic approach that they are taking to address this. Jay is the principal mining engineer with the National Institute of Occupational Safety and Health under the Pittsburgh Mining Research Division. So I think for those that had an opportunity, you managed to read through the abstract and know a bit more what Jay will be presenting on. So thank you once again for making time. We will have a Q&A session right at the end, and that will be handled by my colleague Conchita, and you'll have a chance. But in the interim, you can be typing questions as the webinar progresses, and those will be attended to again. So Jay, over to you for your presentation.
Okay, thank you very much, Cledwin. And let me bring up my presentation here. Okay, can everyone see that okay?
Yes.
All right, thank you. As he mentioned, I would be talking about the status of black lung in the US and then a systematic approach for controlling respirable coal mine dust. First, I'd like to thank Dr. Von Holt for making the invitation, extending the invitation for me to speak today, and I'm happy to share this information with you. Just a quick outline of topics. I'd like to briefly talk about coal workers' pneumoconiosis and silicosis, show you some of the impact that that's had in U.S. mine workers in the industry, talk about 2 dust regulations that are pertinent to the mining in the U.S., some sampling methods that you might not be aware of for coal and silica dust, and then they go through the systematic approach for controlling respirable dust and some sources for additional information. So coal workers' pneumoconiosis or black lung, as I'm sure you're aware, results from the inhalation of respirable coal mine dust, for which in the US is considered less than 10 micrometers in size. Of course, the dust damages or destroys lung tissue. There's 2 forms of coal workers' pneumoconiosis, simple and complicated, with the complicated known as progressive massive fibrosis. The International Labor Office has developed standards which are used to determine the severity of CWP. And once contracted, it cannot be cured, so preventing respirable dust exposure is the key. And you can see on the bottom of the screen, there are 2 lung sections, the left one showing simple CWP, where you can see coal dust deposited in different spots in the lung, and the right lung section showing progressive massive fibrosis with the large areas of damage that have occurred to the lung. This is a brief explanation of the ILO system of classification. Simple CWP is classified numerically between 0 and 3, while PMF has letter designations for severity of A, B, or C. The left radiograph or X-ray shows a healthy lung, which when expanded with air, the lung shows up, if it's clear, as black, while bones and organs show up as white in the X-ray. If you move to the center X-ray, you can see this cloudiness scattered throughout the lung, and that's the coal dust that has deposited in the lung. And then the right X-ray shows those large areas of damage from progressive massive fibrosis, where there's huge areas of the lung that no longer function properly. So before 1969, there were no coal dust regulations or sampling requirements in the US, and this was the first legislation to address that. This act established the 2 milligram respirable dust standard. It defined sampling requirements for both mine operators and federal inspectors. It required NIOSH to establish an X-ray surveillance program, which is called the Coal Workers Health Surveillance Program. And it also established a federal benefits program for miners that are disabled by CWP. So information from the NIOSH Coal Workers Health Surveillance Program is shown here. And this shows miners that have been diagnosed with category 1 or greater and the tenure in mining. And not surprisingly, the longer you work in a mine, the greater your dust exposure and the more likely you are to develop CWP. And you can see when the first X-ray surveillance program started in 1970 to 74, it took about 5 years to cover the whole mining industry in the US. About 1 out of every 3 miners that had worked in the mines for 25 or more years developed CWP. And again, remember that in 1969 was the first legislation that regulated coal dust. So their exposure was with no dust regulations in place. Then over the next 30 years, you can see a steady decline in the prevalence of CWP that was found in the miners that volunteered for this program. It is a voluntary program. And it dropped below 5% for the longest tenured miners in the 95 to 99 surveillance period. Unfortunately, over the last 20 years, you can see an increase in CWP. So the last round, approximately 14% of the miners that were examined had CWP. Likewise, if you look at these same miners and evaluate their X-rays for PMF determination, you can see again very high level at the outset of the program, and then again a drop to the 95 to or 90 to 94 period where the low point was reached. But unfortunately, again, since that time, there's been an increase in PMF, and over the last 10 years, over 1% of the miners examined in the program have developed PMF. I mentioned the federal Black Lung Benefit Program. It provides monthly compensations to miners that are disabled by CWP. It also covers the medical expenses for treatment of the lung disease related to CWP. And when these miners pass away, it provides compensation to the survivors. And you can see here in red the total payments of this program from 1971 through 2020, 50 years, $47 billion have been paid out, and the mining companies have to pay into this fund based on their production levels. And you can see for these miners that are totally disabled, there's a higher percentage of PMF found, but again, the same upward trend over the last 20 years or so. And also the number of deaths related directly to CWP or the underlying cause. You might die from heart failure, but that could be related to the extreme pressure put on your heart trying to compensate for your ineffective lungs. The total number of miners in the US that have died have been 75,178. So human and financial costs have been tremendous. There's been a number of reasons speculated as to why this increase has been occurring, and one of those has to do with silica exposure. Crystalline silica or quartz is more toxic than coal dust to the lungs, and inhalation can lead to silicosis. There's 3 different types of silicosis: chronic, accelerated, or acute. And it basically the dose that you're exposed to and the frequency determines which one of those you are classified as. Again, there's a simple and complicated form of silicosis. And when you look at radiographs or X-rays, the opacities that show up can be classified, and R-type opacities are associated with silica exposure and silicosis. And you can see in the graph on the bottom right there, in a certain region of the US, the percentage of R-type opacities found in miners' X-rays has shown a significant increase over the decades. And this is for what's called the Central Appalachian region, which is primarily 3 states in the United States. It's West Virginia, Virginia, and Eastern Kentucky. And this region has a lot of continuous miner operations, and a lot of the, I would say, prime coal seams have been worked out, and they've moved on to less desirable or lower coal seams. And subsequently, it seems that they're cutting more rock for equipment clearance. And there's some lung sections there showing you the simple silicosis and PMF. As a result of the upturn in CWP and silicosis, MSHA, the Mine Safety and Health Administration, which regulates mining in the US, passed a dust rule in 2014. Part of the rule became effective on August 1st. It requires full shift sampling. Under the previous 1969 rule, sampling was only conducted for 8 hours, even if it was a 10 or 12-hour working shift. In the new rule, for it to be a valid sample, 80% of the average production over the last 30 shifts has to be met. This was only 50% in the previous rule. Also, single samples can trigger action under the new rule. In the previous rule, there was an averaging of samples. So for operators, if they get a sample that exceeds what's called the excessive concentration value, the ECV, and for a 1.5 milligram per cubic meter standard, the ECV is 1.79. That takes into account weighing and sampling errors. If they get a reading that's above that, a single reading, they have to take corrective action. Also, MSHA can now cite non-compliance on a single sample. This rule specifies 100 micrograms per cubic meter as the limit for silica. It was monitored indirectly under the previous rule. And if you exceed that, it reduces the dust standard that you have to meet. And this rule also added surface miners and spirometry testing to the NIOSH surveillance program. Then effective on February 1st, 2016, underground coal mine operators had to start using a continuous personal dust monitor for compliance sampling, which is optional for surface mines. And then effective August 1st, 2016, the respirable dust standard was lowered to 1.5 milligrams per cubic meter. If you're not familiar with the continuous personal dust monitor, this shows it here in the center, or the left photo shows the unit, which has a inlet that clips to the lapel, and the unit's worn on the miner's belt. The principle of operation to determine mass is called a tapered element oscillating microbalance, which is shown in the center. And it's a hollow tube where the filter is mounted on top of the tube. And this tube at the beginning of the sampling is vibrating at a known frequency. And as dust-laden air is drawn through the filter and through the tube, the filter captures the dust, which changes the frequency of vibration, which is directly related to the amount of mass that's been deposited on the filter. So that's the methodology that's used to determine concentration. There's a heated air circuit in the unit, and also the TEOM itself is heated to drive off moisture. And the unit also monitors multiple operating parameters, such as airflow quantity, heater temperature. If the inlet would be accidentally pulled off of the miner's lapel and fall into a pile of dust, you're going to have a large mass gain, and it monitors that. And it will issue what's called status codes if it thinks something is not normal in the operation, to alert the operator. It records dust concentrations and operating parameters each minute. And there's 2 data files that are created: an encrypted data file that the mines have to transmit to MSHA for compliance determination, and then a comma separated value file that can be used for analysis by the mine. The outputs from the CPDM, if you notice, there was a screen on top of the unit. The first screen that comes up is shown on the top here. It gives you the last 30-minute dust concentration and also the cumulative concentration from the beginning of the shift to that point in the sampling period. You can scroll to the second screen, which shows the shift limit, which defaults to 1.5 milligrams per cubic meter, the standard. However, if your operation is on a lower dust standard, you can enter this number in when you're programming the unit for sampling. And under that is a key piece of information. It's the percent of the limit that you've reached. So if you're 2 hours into a 10-hour shift and it shows that you're at 42% of your limit, you know you're on your way to an overexposure, and hopefully you can make changes to control technology or mining practices throughout the remainder of the shift to prevent the overexposure from occurring. The third screen is a bar chart of each bar represents a 30-minute dust average. And you can just look at that to see when the highest exposure occurred during the shift. The graph on the right shows testing from in our longwall dust gallery where we were looking at control parameters. So we'd run some dust for a while, adjust the controls, run another test, and that's what the 3 peaks are there. And those are the 30-minute average concentrations during each of those test periods. And then the blue line is the cumulative concentration. And you can see it tracks up when dust is being sampled and then starts to come back down when there's lower dust levels. So that's the type of information. These could be 3 different cuts in a continuous miner section. And then the mine could look at what the differences are between the first and the second and third to result in different dust levels. In the US, for compliance determination for silica, the 100 micrograms per cubic meter standard, MSHA takes compliance samples. They send them to a lab. It's located in Pittsburgh for analysis. Fourier transfer infrared FTIR analysis is used to determine the silica content. That information is sent back to the MSHA district where the mine is, and then the MSHA district transfers that information to the mine. This whole process can take a week to 10 days. So if there is elevated silica in the mine, the workers would continue to be exposed to that for that 7 to 10 day period before they even knew. So NIOSH was looking for a way to speed that up, and we came up with this end of shift silica analysis technique where you look at a portable FTIR, and we tested 4 different units from different manufacturers. Those are shown in the photo. You use that in the laptop. The FTIR units measure the center portion of the filter cassette. So we worked with a filter manufacturer to develop the cassette shown in the bottom there. It's a 4-piece cassette, and it results in a more even distribution of dust on the filter. And also, since it's a 4-piece cassette, you can take off the top section and the bottom section. The filter's contained in that center tape section. You can then insert that into a 3D bracket that we designed, and those files are available on the government website. And you insert that into the unit and hit the button. And about within 5 minutes, you know what your silica concentrations are. NIOSH software, it's called FAST, Field Analysis Silica Tool, takes the output from the FTIR unit and converts that into concentration. So you know what your silica levels are within 5 minutes of starting the analysis process. And also I should point out it's a non-destructive analysis. So if you wanted to take the filter back out and send it to the lab for your standard type analysis, you could do that. And that would give you a correlation between what you're seeing from the portable FTIR and the lab analysis. So hopefully this would allow mines to make adjustments on the very next shift to prevent elevated silica exposures. And now I'd like to move on and talk about a general dust control approach for reducing exposures for workers. And I'll go through each of these steps and provide you some examples The first would be to minimize the quantity of respirable dust that's generated. If you don't create the dust, you don't need to use other means in order to control it. And you minimize that through efficient cutting. So how do you do efficient cutting? We've done studies in the past looking at different bit designs. And what we found is bits with large carbide inserts or tips that have a smooth transition to the steel bit body result in less dust generation. Obviously, too, the center photo on the top shows a bit on a long wall shear, and the carbide tips missing. And then the two bits on the right on the top, the one on the left, we actually picked up during one of our dust surveys when the crew shut down to change bits. Obviously, this bit was should have been changed long ago, as nearly the whole bit body was worn away. And all that is going to do is scrape and grind against the coal and rock and create much more respirable dust than a sharp bit. Cutting drum design, depending on your conditions, the vein number of veins, the vein angle, the vein depth, bit spacing, drum RPM, they can all have an impact on the amount of dust that's generated. And most drum manufacturers have programs that for your conditions can help you design a drum that will result in efficient cutting and loading. And then, as I mentioned, in the Central Appalachian region of the U.S. mining industry, a lot more mines are cutting rock. And one of the things that you can do if you do have to cut that roof rock is undercut it, as shown in the left drawing there on the bottom, and then back up and cut the rock. And what this does is allows that rock to break out to what's called a free face. It's not confined by the coal underneath of it. And that results in less fines being generated during the extraction of that rock. Once you have efficient cutting, the next thing you want to do is prevent the respirable dust from getting airborne, the dust that is generated. And you do that through wetting the dust and enclosing the dust source. So wetting the dust, you're going to use water sprays. There's a number of different types of sprays that are found in mining, and each of the sprays is best suited for a certain type of control. And here's the three ways you can use water sprays to control dust. Suppress the dust, again, prevent it from getting airborne. You can capture it out of the air, or all sprays to some degree induce airflow movement, and you can use the sprays as kind of like small fans to redirect the dust. You can see I put the capital letter behind each collection method. And then for the sprays shown on the bottom, added these letters to show what spray is best suited for what type of collection. So for suppressing dust, full cone, flat fan, or solid stream sprays are the most effective from suppressing. And when you want to suppress the dust, water quantity and full coverage are the key. You necessarily don't need high pressure sprays for this type of control. And you want to place the sprays near the dust generating source. So as shown on the bottom left, longwall shear drums, the sprays are located either directly in front or behind the bits. On the continuous miner in the center, sprays are typically located immediately behind the cutting drum on the boom, or now there are wet head sprays that can be located in the cutting drum itself. And then for surface operations, if you're doing wet drilling with tricone bits, if water makes it to the bit, it can lead to shortened bit life. But one way you can get water there and near the cutting zone is this water separator that separates the water from the baling airflow and discharges it into the drill holes, where it can mix with the dust as it comes back out of the drill hole. And then the schematic on the top right is a longwall face conveyor and crusher stage loader. And you would want to put sprays before the material hits the crusher, immediately after it leaves the crusher, because you're creating new dry surfaces that need to be wetted, And then also you could add sprays before it gets transferred to the conveyor belt to try and provide additional wetting. On surface mines, haul roads can generate significant amount of dust. You can see in the top left photo, the dust that's being generated by that haul truck. And in the green rectangular box, there's actually a pickup truck near the side of the road. So in addition to a health issue, it can be a safety problem if visibility is affected. The top right graph shows this road that was watered at 10 o'clock. You could see for a couple hours while it was still wet, dust levels were low. But then as the road dried out, it started to increase in dust as the trucks went by our sampling location. And wetting can be done with dedicated sprays as shown in the photo on the left on the bottom, or a simple manifold that has holes drilled into a pipe as shown on the right. I mentioned another way to prevent the dust from getting airborne is enclosing the dust source. The photo on the left shows a crusher stage loader unit. This is new from the manufacturer. When I first started doing sampling on longwalls, where it shows the system enclosed up there, that was open, and the mines would have to try to enclose that. You can see now that's completely enclosed by the manufacturer. Belting is installed at the inlet to the crusher and also at the discharge to the section conveyor belt. On surface operations, when haul trucks go to dump their load, wherever they're dumping into the primary dump, the volume of material in the truck is going to try to displace that same amount of air, which tries to come up and exit the primary dump. And you can use what's shown on the top, these staging curtains, to try to dampen that airflow, or plastic stripping as shown in the bottom right. Also on surface mines, one of the greatest sources of exposure is the rotary drill or high wall drill. And the dust is generated by that bailing airflow coming up out of the hole, carrying the dust with it. So what you would want to do is completely enclose that drill table with shroud shown in the left, and that'll allow the dust collector to capture as much as possible. The graph on the top right shows some tests we did in our laboratory where we looked at different collector to bailing airflow ratios. And obviously, the more collector airflow that you have above the bailing airflow ratio, it's going to be better, as shown here with the 4:1 showing the lowest dust levels. But also what this showed is we changed the gap between the shroud and the bottom of the ground. And you can see as that increases, dust escapes much more readily, even at the higher collector to bailing airflow ratios. Another point of leakage on surface drills is around where the drill pipe goes down through the drill table. There's a bushing there. It's fairly tight clearance initially, but as it wears, it allows the bailing airflow to blow right back up through the drill table, as shown in these two photos on the bottom right. You can see the dust cloud just coming up out of the drill table. The next thing you want to do in this approach would be to remove the respirable dust from the ventilating air. You can use dust collectors or water sprays to do that. One of the most effective controls that are used in the US are called flooded bed scrubbers, where they pull dust-laden air in near the face through ducting on the miner, back through a wetted filter panel, a mist eliminator to remove the dust-laden water droplets from the air, and then the air is discharged back into the mine entry. Testing we've done show that there's over 90% collection efficiency can be obtained with certain filter panels. However, the overall efficiency is a combination of the capture efficiency, which is the amount of face air that's drawn into the unit, and then the collection efficiency. And over 90% of continuous miners in the US are equipped with flooded bed scrubbers. We've done a number of tests on scrubbers. The most recent, we looked at the filters that are used probably 10 years ago when we did these tests, which were shown in the photo on the bottom. And not surprisingly, the more dense the filter is, the better the dust collection. As you can see here, all these filters are stainless steel layers. And there was a 30 layer, a 20 layer, and a 10 layer at the time being offered. And you can see the 30 layer had 93% collection efficiency, which dropped to 74% for the 10 layer. There's a trade-off though. The more dense the filter is, the greater resistance it has for the fan, and you're not going to pull as much air through the system. And that's shown with the blue lines and blue markers there. So it's a balance between moving air through the system and collection efficiency. One thing we have learned recently is that the manufacturer is no longer offering the 10-layer filter. I guess that's because of the low collection efficiency. Most roof bolting in the US is done with the dry dust collection system, where the dust is pulled through the drill bit, the steel, the drill head, and hosing back to what's called a pre-cleaner, which is basically a cyclone that's designed to remove larger material from the airstream before it goes into the collector box, where there's several different channels, another cyclone, a final filter before the filtered air is discharged through the muffler back into the mine entry. We've done numerous studies on this type of system to show that they are very effective when operating properly. One of the problems is that dust collector box fills with dust, and it has to be periodically cleaned throughout the shift, oftentimes after every place that has been bolted. And if it's really full, when you open the door, like in the top left photo, dust just kind of falls out immediately. You can see a dust cloud being generated, maybe getting on the workers' clothing. Historically, what would happen then is the roof bolter operators would reach into the unit with their hand, a wedge or a small steel scoop, and scoop out the rest of the dust. The manufacturer then came out with this pull-out tray that's shown in the top right. And what's been developed over the last dozen years or so are these collector bags, which are shown on the bottom left. And it's like a bag that you might use in a vacuum cleaner at your house, where you can retrofit the system to existing bolters, or new bolters are offered with it. And you basically insert this bag into the large chamber in the collector box, and the majority of the dust is collected within this bag. It does two things. When you go to empty the collector box, it's all confined, so you don't get that dust working on or contaminating your workers' clothing or creating those plumes in their breathing zone. It speeds up the cleaning process, and it also reduces the loading on the final filter, so that doesn't need changed quite as often. And a new system that we've just evaluated within the last, prior to the pandemic, is a wet collector box, and it goes from a dry system up at the drill head and drill system back to the collector box. But in the collector box, a water spray is added, the internal cyclones removed, and you can see the shape has been reconfigured with angled walls that are trying to direct the material towards a drain plug that's added in the bottom. That can be activated by the operator periodically. And what happens is the dust enters, water sprays it, it becomes this slurry that's shown on the bottom right photo. And periodically you need to open up the box and spray out the rest of the material that hasn't drained through the hole. The manufacturer has also gone from the standard final filter, which was a paper filter, to a water resistant filter. And this proved to be very effective, and they're requesting approval for this through the Mine Safety and Health Administration. Another technology that we've developed and tested in multiple mines is a canopy air curtain. And the principle of this is shown in the schematic in the top left, where you put a centrifugal fan on the machine, pull a portion of the ambient air through a filter, and then blow that filtered air down over the roof bolter operator while he's under the drilling canopy. Initial testing showed a 53% reduction. There's about 50 roof bolters now in the US that are equipped with a canopy air curtain. You can see it installed on the machine on the left bottom photo there under each canopy. And we've just recently, again, before the pandemic, tested this on a Ram car with blowing face ventilation, because shuttle car operators or Ram car operators with blowing face ventilation are in the return air of the continuous miner. And while they're loading, that's the greatest dust exposure that they get. And we installed this unit. You can see the orange unit installed there on the operator's cab on this Ram car. And we got a 65% reduction during loading when it was behind the continuous miner. Another effort to prevent exposure when the roof bolters are downwind of the continuous miner was this standalone dry scrubber. You can see in the schematic, you would place this unit in between the continuous miner and roof bolter operator to filter a portion of the air that's then directed up to the roof bolter operators. The prototype is shown in the photo on the right. And one of the keys to this, it has two large filters in it, but the operator sets the desired quantity of airflow that you want for a cut. Program that into the machine, and then there's a variable frequency drive fan that will monitor that airflow and automatically adjust the fan as the filters load up and the resistance increases. So it is designed to maintain the set point airflow that you put in there. In our underground testing on two different longwall or continuous miner sections, we saw over 50% reduction in the face dust levels. Dry dust collection systems on surface drills, I mentioned this previously. Again, they can be effective if well maintained. And one of the keys, again, is to have this shroud as close to the ground as possible to prevent that leakage that's shown coming out from under the shroud. And I also mentioned the leakage around the drill stem bushing and showed that in some of the photos. Water sprays for airborne dust capture. In this application, you want sprays that produce smaller and higher velocity droplets. The schematic on the left shows why. Say the water droplet in this photo is 100 microns in size, and you're trying to capture a 5 micron dust particle. As that droplet's moving through the air, it creates these air streams around it, and the dust particle could follow that airstream and never contact the water droplet, so obviously it wouldn't be captured. With the smaller droplet shown on the right, there's a greater chance for those two, the droplet and the particle, to interact and capture one another, which would then allow it to fall out of the airstream. We did testing in a dust box at our lab, and you can see on the right, the graph shows that atomizing sprays and hollow cone sprays were more effective than flat fan or full cone sprays. That's because they produce smaller and higher velocity droplets than the other two types of sprays shown there. The other thing this graph shows, that regardless of the spray type being used, if you increase the water pressure, that's going to increase the or decrease the droplet size, and increase the velocity of those droplets, which will lead to more efficient capture. Once you've minimized the quantity of dust, prevented as much from getting airborne, and removed dust from the air, anything that's remaining, you want to dilute that as much as possible. And you do that by increasing your ventilation quantity and increasing the distance from the source of dust to the workers. So on long walls, particularly in the US, we have all retreat longwall mines. So the conveyor belt entry is bolted during development. So when the longwall is retreating, the bolts in that entry often allow the gob to stay open a little longer than the rest of the face, as shown in the top left schematic. And this will allow airflow to flow directly into the gob. And even if the air then comes back onto the face, it can pick up dust and methane, which you obviously don't want. So a simple solution is just to put a gob curtain in there, shown in the top right schematic and the photos on the bottom, where you hang Bradis between the rib and the first shield to try to turn as much air down the face as possible. And increasing the distance from the dust source allows that dust to mix with the ventilating air and get more diluted. On longwalls in the US now, that's automated shield advance, which is triggered by the shear position. And as a result, in most of the surveys we've seen, that those shields are moving 1 to 2 shields behind the trailing drum. So on the head to tail pass, as soon as that drum clears a shield, it's advancing forward, which shows a concentrated dust cloud in that photo, then passes directly over the head gate shear operator. So if you can lag that shield movement, if your roof can take that and move it up the face a little bit, that'll allow time for that dust to disperse and mix with the ventilating air. Likewise, on continuous mining sections in the previous schematics I showed, the roof bolter was in the immediate entry downwind of the continuous miner, which is going to be the greatest dust concentration it can see. In this schematic, you can see the bolter separated, and the dust generated by the miner will have to pass through all those faces before it reaches the bolters, and it's going to mix and dilute. Finally, you want to prevent respirable dust from reaching the breathing zone of the workers. If they don't breathe it in, it can't contribute to disease. And this is accomplished with ventilation, velocity, and direction. As I said, sprays move air, so you can use that to your advantage, or physical belting or physical barriers, excuse me. One of the dustier portions of a continuous miner cycle is cutting cross cuts, as shown in this top left schematic. If it's a cut into the ventilating air, the green arrows show the original travel of the air. It's coming around the pillar, up behind the curtain, over the operator, and toward the face. As soon as the miner breaks through, however, into the entry, that air is going to short circuit and travel back over the miner operator and shuttle car operators. So you want to minimize, and that's shown in the graphs on the right, where you break through with the ventilating air, the dust actually goes down. When you cut into the ventilation, it actually goes up rather sharply. So you want to minimize that. And if you, one thing you can do is not break through on the box cut like it's shown in the schematic. Allow a meter of coal or something there, move over, take the rest of the entry, the slab cut, and break through, and that'll minimize the time that the airflow is disrupted. One of the more effective controls for long walls is called a directional spray system, or shear clear, where you mount sprays along the body of the shear and a splitter arm, which is noted there in the drawing. And the goal of this system is to split the intake air that's coming down the long wall face, keep the dust laden air generated by the shear up near the face, while the intake air passes over the operators in the walkway. And this is accomplished with that splitter arm, which has conveyor belting hanging down into the face to create a physical barrier. As the coal loads over the ranging arm and falls into the conveyor, it creates a dust cloud that tries to come up into the walkway. So that physical barrier of the belting and the sprays, and on this arm, there's Venturi sprays mounted. It turns that dust back toward the face, and then those hollow cone sprays that are noted in the photo keep it confined near the face. And then when it gets to the tailgate, you have some sprays that are parallel to the tailgate ranging arm to continue to move it past the shear. And if you look at the two photos on the left, you can see the walkway is very clear. The bottom photo, I was actually standing near the tailgate shear operator. That's the headgate shear operator shown in the photo. And you can see the dust and water mist confined up against the face, and the walkway is pretty clear. Contrast that to the bottom right photo, which didn't have a very good spray system. And you can see the dust rolling into the walkway, and it's going to pass over the tailgate shear operator. On surface mines, physical barriers are provided by enclosed cabs. And also you can have installed, factory installed or retrofit air filtration and pressurization systems to further provide clean air to the operators. And finally, stressing the importance of maintaining controls. One of the things I've worked in the health area for pretty much most of my career, and you can see the difference between a safety item and a health item, where safety, if the roof is a piece of roof rock is hanging, the miners will immediately work to take that down. However, if hose to water sprays is busted, they just might turn the water off and say, well, we'll let maintenance get that at the end of the shift. So there's not that same sense of urgency, but there needs to be. It's critical to maintain the controls for sustaining the best dust exposure for your workers. Here's those bits that I showed earlier. We've done studies. I said flooded bed scrubbers are one of the most efficient controls that you can use. However, we've done 2 or 3 studies that show you can lose 35% of your airflow after only one cut. So you have to maintain the filters in the mist eliminator system. And finally, some additional information. On the left is a publication that we produced in 2010. Talks about the dust controls I've shown here and some others, and it's available on our website. Over the last year and a half or so, we've been updating that publication, which is what is shown in the center. That should be on our website within the next month or so with the new information. And physical copies will be available shortly after that. And then another division of NIOSH, the division that's responsible for the X-ray surveillance program, produced 2 videos, Faces of Black Lungs, what they're called. And the one I'm showing here is the most recent. It was released in 2020. And they interviewed 3 miners. One was 39, one was 42, and one was 47 years old. They all had PMF. And they talked about the impact it's had on their life and their family, and how they had wished they had paid better attention to dust control during their careers. And in fact, the miner shown in the lower left corner with the oxygen, he passed away before the video was released. So with that, that's the information I wanted to present. I would be happy to answer any questions now, or if you think of something later, here's my contact information with my email address. And I appreciate your time and attention. Thank you.
Thank you very much, Jay, for the very comprehensive talk. And it's very interesting to hear how mines can make better choices to reduce dust levels where people work. So I don't know if anybody has any immediate questions. Got some questions to start. So one that I have is epidemiological data in academic literature has shown that there's a regional difference in the prevalence rates of CWP across the US. So I just wanted to know what's the uptake of some of these technologies that you spoke about, and is there any sort of regional differences between the technologies used?
Probably it was about 10 years ago, I guess, when the surveillance first showed the uptick in the CWP and the regional difference. We actually had a project where we wanted to do just that. We looked at mines in that regional area that were having success for controlling dust, and then mines that through MSHA compliance sampling were having difficulty in controlling dust. And we wanted to visit and get information from those mines to see, are there differences in the types of control technologies being used? We went to, I think but each mine in the US has to submit a plan to MSHA that says, this is how we're going to control our dust. And they dictate how much air, types of water sprays, where they're located, the types of controls. And we made a comparison of over 80 of those mines, 40 that were having success and 40 that weren't. And really didn't see major differences in the types of controls they were using. The one difference that we did see at that time is the problem of rock dust being generated because the mines that were having trouble seemed like they were mining more rock in general than the other mines. And that leads to more dust exposure because most, machines are designed to cut coal, not rock.
Mm-hmm.
And that we've also shown that cutting rock, like the flooded bed scrubber, it can load up more quickly and lose more airflow when cutting rock versus coal.
Okay.
So that was the major difference. And the other thing was, like I mentioned before, the maintenance of those controls. It seemed like the mines we actually did visit weren't as diligent in maintaining the controls that they had.
Okay. We have a question from Mohammed.
Thank you, Jay, for that very interesting presentation. I have a question which is twofold. Could you comment on the current occupational exposure limit that is currently being followed by the US and how that compares with international best practice in terms of a safe standard? And the reason that I asked this question is that the current exposure standard in South Africa is 0.1 milligram per meter cube. And the mines have this explicit aim to eliminate silicosis. And this is obviously inadequate. So I would like to know what standard is being used in the US and whether that in itself is contributing to the current disease burden that is being experienced. Thank you.
Yes. As I mentioned, the mines are regulated in the US by the Mine Safety and Health Administration. And currently the silica exposure limit is 0.1 milligrams per cubic meter. However, to calculate that, when the 1969 law was passed, kind of most of the historic dust exposure and CWP data was from England, and they used what was called a horizontal plate elutriator sampler to collect their dust. In the US, we use a 10 millimeter nylon cyclone. As a result, the law said mines had to use that elutriator or an equivalent sampler. And the regulatory agency did sampling at that time that showed, to compare the nylon cyclone to that elutriator, to make them equivalent, you had to multiply the concentration from the cyclone by 1.38, which is called in the standard MRE equivalent concentration. So all the samples that are collected are multiplied by 1.38. So even though it's a 0.1 milligram standard, it's actually more like 0.072 or 73, the actual concentration, and then it's multiplied by that 1.38 to see if it's in compliance. The other thing is, other than the mining industry, the rest of industries and manufacturing in the US are regulated by, it's called the Occupational Safety and Health Administration. And just a few years ago, they reduced their silica exposure limit to 50 micrograms per cubic meter, or 0.05 milligrams per cubic meter. And MSHA has since and continued to work on developing a proposed silica rule that everyone expects would lower the standard. So that's hasn't been released to the public yet, but they've been working on developing a new standard which should lower the limit. Hopefully that answered your question.
So we have another question from Mark Moran, and he asked, what equipment manufacturers are contributing to solving the dust issues on mines?
The roof bolter industry is dominated by one manufacturer in the US. It's Fletcher Mining Equipment. I believe they also sell around the world. They've been very active. They developed, we put out a contract for that standalone dry scrubber. They worked, bid on that and developed that unit. They've worked with us on the canopy air curtain designs, and were instrumental in the ram car testing that we just completed before the pandemic. Also, we've worked with Joy Manufacturing in the past, which is now Komatsu Mining. We've done workshops for them. They visited our full-scale test facilities, provided information and equipment for us to test. So those are the two main manufacturers that have been most active in developing control technologies.
Okay. We have another question, and this reads, one of the factors that contributes to coal dust toxicity is coal rank. Could Jay please explain coal rank?
Well, coal rank, at least as we define it, is the percent of fixed carbon that's in the coal, and the higher the fixed carbon, the higher the rank the coal is. Past studies have shown a link between coal rank and CWP. I mean, excuse me, the highest ranked coal we have in the US is anthracite coal, and there's not very much production of that anymore, but when it was producing, that was one of the areas where CWP was prevalent. So there have been studies that show rank. More recently, other researchers have tried to show links between maybe iron content, bioavailable iron in the coal, and disease development. I don't know that that's been sufficiently established yet. And a couple years ago, the National Academy of Sciences wrote a report looking at dust sampling and the dust control methods in the US. And one of the things they recommended was further characterization of the coal. So we've funded probably 4 or 5 contracts with universities in the United States to try to characterize coal. Is the size distribution getting smaller? Has the content changed somewhat over the last 20 or 30 years? So those studies are ongoing right now. We don't have all the results yet.
If anybody doesn't have any other questions, we've got, okay, we have a question from Johanna.
Hi Jay, nice to meet you online. Thank you very much for taking up the offer to present. I like the way that you say that, the sense of urgency, sort of the health versus safety, sort of a long-term risk versus a very immediate high risk. How successful are you in kind of convincing miners that this is something they really need to treat as, with as much urgency as a safety issue?
Not as successful as we would like, I'm sorry to say, but that is one of the reasons that our other research division, the Respiratory Health Division in Morgantown, developed those 2 videos. Particularly the first video they produced probably in 2008 or so. There was a 55-year-old and a 58-year-old miner that they interviewed, and both of them talked about wishing they had paid more attention to dust. The one miner, his saying was, you can whoosh the dust off of your face, you can't whoosh it off of your lungs, so protect yourself. Those are pretty impactful, and we use those in most of our workshops or training sessions with miners to try to impact their thought processes. And then the reason they produced the second one is they were concerned that, well, a 20-year-old miner is looking at these guys, they're 55 and 58. I don't have to worry about that for 40 years. That's when they went to the second video with the younger miners that were as young as 39 years old, saying, look, this can happen to you at a pretty early age. So try to protect yourself. So those, I think, are effective means of trying to get that message across.
We have a question from Cledwin.
Hi, Jade. Thank you for your presentation. I just wanted to ask a more general question. You've worked with quite a number of these companies to develop technologies that can assist in dust monitoring. How translatable are these technologies and transferable to developing countries where some of us, the side of the globe, and the adaptation of those technologies to countries where maybe finances and the ability to have the technologies might be an issue? Is that something that's in the pipeline as you develop solutions, not only for the States, but maybe for the global arena?
Right. That's one of the issues with the continuous personal dust monitor. Currently, it costs approximately $17,000 US, which is, a big expense for mining companies, particularly if, it's not a large operation or an international corporation. We do have projects looking at what we're calling low-cost dust monitors, but at this point right now, that's looking at surface applications such as coal preparation or mineral processing plants, because they're not approved for underground use. And they were initially designed for more of ambient air, environmental protection versus personal. So these only cost in the hundreds of dollars, but we're not sure how they work on mine level dust concentrations. So that research is currently underway. It was delayed some by the pandemic, but it's ongoing.
Okay. I'm not sure if any, Tedwin, do you want to follow up quick with another question?
Yes, sorry, Jade, to just make a follow-up on that one. Maybe just out of interest, rough timeline guides, because if you look at this other side of the world as well, global south, you tend to also have semi-formal and quite a lot of informal mining. So if it's expensive for big corporates, getting to semi-formal or small to medium enterprise miners, and then maybe to the informal miner, might be some decades away.
Yeah, I can't argue that. At least in the US, one of the battles for this is the underground coal mining market was never huge from a general manufacturing standpoint. And it's even shrunk. Production is probably 60% of what it was 10 years ago. So it's difficult to induce manufacturers to look at that market, particularly when there are specific requirements that they have to meet. Like MSHA has the intrinsic safety requirements that MSHA has to test all these instruments so to show that they're safe to use in the methane environment in the coal mine, which is another hurdle that a lot of manufacturers don't want to take on, just because of the potential market they see on the other side of not being as big as they would like. And the other thing, like the continuous personal dust monitor, I know in talking to that manufacturer, they're trying to make it globally available, but there's different standards, and I'm sure in South Africa, Australia, China has certain regulations with types of batteries that can be used. The normal battery can't be used. So those are all challenges that all these manufacturers face in trying to get something globally available at a low cost.
So we do have one more question. This states the current LEL of 0.1 microgram per cubic meter used by the MSHA and indeed also adopted in SA. How was it arrived at? In other words, was it anecdotally or experimentally arrived at? And how effective, assuming a mine operates within it, is it in the prevention of a disease?
I can't answer that really. I know from the 1969 Act, before I was obviously involved in mining, that was always the standard. I don't know exactly where that number came from, if it was just an empirical number or if there was some medical data that, you know, suggested that that might be sufficient for protection. And yeah, I just don't know. I know in the US, there's a large silica sand industry, which they're basically mining pretty much pure silica. And they try to keep their levels at 50% of the existing standard, just to try to provide a margin of safety. And again, OSHA has reduced the standard from 100 micrograms per cubic meter down to 50. So that, I think, is the next expected level in the US mining industry.
Thank you very much, Jay, for coming to present and for taking on the questions. And would like to also thank all the participants who managed to join in live for this webinar. And I think we'll have more of you, Jay, joining us in the future, I hope, for updates on how much progress this research would have gone with the NIOSH. So with
And again,
that,
thank you for having me, and I've enjoyed, you know, trying to share some information with you.
thank you very much, Jay. And thank you very much to all the other participants. So until our next run of the Mine Dust Network Forum in conjunction with SAMM, we hope that you will be with us again. Thank you.